Welcome back to class. We have everybody back to class today. And we are to the section of the course that has to do with optimization. And I'm starting out with this problem today because I think this is kind of an interesting problem, and I've actually been thinking about this sometimes, that you have a situation where you have a swimmer out a long ways from the shore, and actually 1 mile from the shore, and then here this distance is 3 miles. And if you do the thought experiment, you know the swimmer could swim, as a swimmer you could swim directly to town, but because you swim at 2 miles an hour and walk at 4 miles an hour, you know just with your thought experiment that's not going to be your optimal course, because you're going to want to have a lot of time walking is going to be your most optimal course. But then if you go straight perpendicularly to the shore, you know probably that that's not going to be exactly optimal either. Your optimum point of landing is going to be to go somewhere in between that's going to minimize the amount of time it takes to do that. And I think this is a little bit of a challenging problem to set up, so I just want to kind of work with you on this a little bit. Now, you're going to try to minimize, and in order to minimize, what's the concept that you're going to do with the calculus? What is the calculus that's going to make the minimization happen?
Why is looking at me?
What do you think? In optimizing, what are you trying to do? Yeah, so what you're going to do is you're going to have some kind of a relationship like this. I don't know if that's exactly what it's going to look like, but what are you looking for here? If I draw a graph of this, what are we looking for here? Yeah, you're looking for your minimum here, and how are you going to find the minimum?
You use the what's it called?
What kind of number are you looking for? Oh, we've been talking about it for many weeks now.
It's on the tip of my tongue.
Starts with a C. We're looking for a critical number. Okay, so let's go ahead and figure out how to do that. Well, here we want to find an equation for time. And how do you get an equation for time out of this? You have swimming at 2 miles an hour and walking at 4 miles an hour. How do you get an equation of time out of this? Yeah, it's kind of tough. So basically what you have is if you have 1/2 hour per mile, is that right? So 1/2 hour per mile, and how many, and when you walk, how many hours per mile is that? 1/4 hour per mile. Okay, and then you want to optimize, you want to have the right landing, you want to know how far from shore it is. So how do you determine these distances that would be, what would be this thing right over here? We want this distance right here. What is this distance going to be here?
3 minus X.
Yes, it'll be 3 minus X. Right, 3 minus. Is that what you, Kylie, came up with that? Yeah, good. Okay, and what is this distance here going to be?
That's gonna be wouldn't that be something goofy like? Oh, it'd be yeah. Do you have to use what do they call it?
Yeah, the most famous formula in algebra, Theorem theorem, right? So you're going to have here the square root of 1 plus x squared. And so now you're going to get here's going to be your distances. So what is going to be your total distance, or your total time? It's going to be what? This distance times the amount of time. Well, how many in swimming? What do you have? 1/2 hour per mile. So 1/2 times this, and what goes over here?
Plus.
3 or 1/4.
Quarter. And this distance here, 3 minus x, right? Now, to me, what has happened here, to me, is the hardest part by far of the problem, to set it up like that. Because to me, it's not super intuitive. You have to sort of think through this thing and all this. Do you agree with me? That does not seem. Now, Connie was able to figure out that distance on land pretty easily, and then we worked through that. To me, that's not the hardest part is this part right here, to figure this out. So this is a word problem that I think is quite advanced, but I think it's quite interesting, because it's the kind of thing that you can see, yeah, maybe I would be interested in figuring that out. And so now what are we going to do with this thing here to find our critical numbers?
So equals zero.
What is the definition of critical number?
The number that is equal to 0 and
So where the derivative is equal to 0 or undefined. So what do we have to do with this thing?
find the derivative.
Find the derivative. So I want you to, and set it equals 0. So I want you to do that with this equation, and go ahead and find the derivative and set it equal to 0. See if you can find what x is.
Oh, thank goodness. Yeah, let's just do that.
Yeah. Let's just casually find the derivative of that. You see what you do, the problem is.
I'll give you a little hint on this one here.
Excellent.
Not that you really should need that hint, but how about if we just do this and make this to the 1/2 power? How's that?
Oh, now it's so easy.
That makes sense better. A little bit. Are we good?
I'm gonna do it, and then I'm gonna let you finish it, and I'll tell you if you got
Okay.
All right, let's try it. I'm not gonna promise much.
I'm not gonna promise the right answer, but I'll try. I'll try to.
That's good. That's what I asked you to do today.
Okay, well, why can't I just? Can't I do that? Sorry. I'm trying to like also do this.
I got like x equals plus or minus square root of 1/3 of a mile. Does that look right?
Yes.
That's where I was getting.
That's where you're getting? But it's just like a process, and then that's going to be square root of 1/3 of a mile. It's going to be, what is that going to be when you work out that? It's going to be, how many, I want to decimalize it. I get a better picture if I decimalize it somehow. So square root of 1 divided by 3. It's going to be about 0.577 miles. So you're looking here, 0.577 miles. Okay, so let's go look back at here. So you're saying this is going to be about 0.577 miles, this distance here, and so this is going to be, that's going to be, what distance this is going to be? It's going to be square root of 1 plus x squared. It's going to be bigger than that. And then this will be 3 minus 0.577 miles. So that's all I want to spend with that problem. I want to go to a couple more problems in optimization today. And ones that are easier. This one is not bad. The ones where they give you the equations are, to me, easier because you don't have to set things up. Okay, you have to do a couple more of these. Okay, I want you to do this problem right here, economic optimization problems. And one reason I want you to look at this is because on your final there's going to be a problem that's going to be similar to this, where you have given an equation and you're looking for, in this case, a maximum profit. And sometimes you'll see these being a minimum cost too. So I want you to go ahead and work this out. I think it can be done without a calculator. But what is the process on these problems to do what? Yeah, what is your process on optimization?
Oh, yeah.
Find the derivative, set that derivative equal to 0, solve, and then you'll have your critical number. And then with your critical number, you can use your critical numbers. And remember the extreme value theorem? So the critical numbers you evaluate, and what other numbers do you evaluate besides your critical numbers in the extreme value theorem?
I do not remember that.
Okay, well, you have your endpoints. In this case, you're not given any endpoints, but in your endpoints, you'll be given like a restricted domain. Let's say they restricted the domain from, well, practically what you have is a restricted domain here, because you know you're going to start with 0, right? What amount of advertising? So 0 is your minimum advertising, and then you could conceivably have unlimited amount of advertising. So this will be your practical domain of this situation. Go ahead and do that, and we'll go over the answer here in a couple minutes. I see some right hands. Yes.
On the final, are you planning on putting a curve on that question?
Yes.
Well, kind of probably, but it sort of depends on how it gets out. I don't have exactly an idea of what that's going to be.
If we're doing it where I'm the lowest, if there's gonna be Aaron, get some questions on our purpose. Mr. G, can I go to the bathroom?
No.
Are you, oh, I guess you are.
Okay, what is our derivative of this?
I'll go with
P prime is equal to,
you.
It is 20 minus X.
that's 20. We have minus 2 times 1/2. So we have that. So where do we set, what do we do with this now? So what are we going to get here? S is equal to what?
20.
20. And so, in hundreds of dollars, so advertising is how much? $2,000. Now, are we 100% sure of that answer?
Not necessarily.
Not necessarily. Let's go ahead and see if we can. Go ahead and put P prime, P, see if that works, right? That's our critical number. So what's a number that's less than 20?
0.
0, right? So that'll be 20, that's going to be positive, right? What's a number greater than 20?
40.
40, right? And that's going to be down. So is this going to be our right answer?
I believe so.
Yeah, okay. So just, that number line is a quick thing, and so I want you to look at another problem here quickly before we get into the next thing.
Yes.
I want related rates.
Mr. G, can I please go to the bathroom?
You may,
I may.
Not.
I'll give you one more to do here. Oh, here it is, this one right here. 3 is ball thrown straight up in the air from ground level. 1 is the ball reaches maximum height. What is its maximum height? Now this problem is pretty much the exact same problem that I gave you to do last year in pre-calculus. In fact, first semester of pre-calculus, we did this thing and was tested on it at least twice.
Where's that at?
It's back from where the
Oh, okay.
was, right? But on your test last year, what did you have? What were the expectations last year for a problem like this?
You put in a calculator.
Yeah, put it in the calculator, graph, trace a graph, or possibly look at a table. Same procedure, so the first step is S prime of t is equal to negative 32t plus 50. And then what next? So 0 equals negative 32t plus 50. So 32t is equal to 50. And then solve for t. So t is equal to 25 over 16 seconds, right? So that's going to be our answer. And does that answer make sense?
Yes.
It really does, kind of. And then what is its maximum height? Well, we have S of 25/16. It's going to be equal to negative 16 times 25/16 squared plus 50 times 25/16. Now, I don't know exactly what that is. To me, this is a calculator thing, because you could do it without a calculator, couldn't you? But then you're really talking about some fractionalization. So we'll just leave. This is going to be our time. This will be max height, right? Okay, so that's it.
Nice.
Yeah, so shouldn't be too bad of a problem. All right. On your final, the optimization one you're going to have is a formula that you're going to minimize cost. So it's the same process. Take the derivative, set that derivative equal to 0, and solve, and you'll be able to obtain the minimum cost. Okay, what I'm going to do is, next section of the book is related rates, and we're going to actually come back to this probably in January, and so we're going to skip temporarily and go into
Antidifferentiation.
this next section, which is, we're about there, antiderivatives.
Yes.
Okay, 37. A function big F of x, and here we're talking about a little bit different notation. A function big F of x is an antiderivative of function little f if f prime of x equals little f of x for all x in the domain of f. So basically what this is saying is that reset my there we go. I don't know what happened with my pen. But basically it's saying that if you take the first derivative of big capital F of x, you will get little capital F of x. And the process of finding an antiderivative is called antidifferentiation. And then part 2 here, the family of all antiderivatives of function little f of x is called the indefinite integral of f with respect to x, and is denoted by this thing right here, this integral symbol f of x dx. And that's called an integrand. And it says if big F of any function such that big F prime of x equals little f of x, then the integral of f of x dx is f of x plus c, and it's called the general solution, and c is called the constant of integration. And that, it's a constant, it is just a number. And that number could be, what does arbitrary mean?
It doesn't matter.
It could be anything. It does matter, but it could be, in this instance, it means it could be anything. And so, if you don't have additional information, some information, then you have to use an indefinite integral. And the definite integral comes when you're given numbers that you can pin it down to something definite. And I'll explain why. I think it has an exercise to help you understand why. Okay, and here's that exercise. State three functions, big F of 1, little f, big F of 2, big F of 3, whose derivatives are f of x equals 3x squared. So I want you to find three functions. So it's a process of you trying to work at finding what the antiderivative is of that.
Are you going backwards?
Yeah, so you're going backwards. So I want you to just find one. Find one function. And then we'll talk about getting three. Note card 37.
Whoa. I think I got one.
Okay,
I
Kylie.
got one.
You got one? Okay. We'll tell you. So Kylie has one. This is going to be Kylie's.
Oh, I don't like that. Now I mean it's wrong.
No, that's fine, because what it is, I want you to go ahead and,
written it down.
Who's in my head?
That's the one I got.
yeah, so what did you get, Kylie?
X to the third?
So, you said f of 1 equals x to the third power, okay? Does that work out if you take the first derivative of this? Does it give you that?
Yeah, it does.
Okay, so that's going to be one example. One example, and then it says, that's the same one you got, Aaron?
I was to say, yeah.
Okay, anybody get another one, f of 2? Is there another one you can think of?
Well, why can't it just be like x cubed plus 1?
Yeah, so let's go ahead and put x cubed plus 1. So this is Aaron's second example. Okay, so now we have two of them. And can somebody else give us an example for f of 3?
You can, Mr. G.
No, you can.
I can't. You can. I'm ready.
Carson, do you have-
I want to see what you've learned.
What is it? Do you have an example, Carson?
No, I didn't know.
Kyla, do you have an example of f of 3?
No.
I'll give you one. I'll give you x cubed minus 50,001.
That's a fun.
X cubed minus 50,001. Now who could give me another one? Who can give me f4 equals what?
X cubed. How about plus pi?
Plus pi, okay, yeah, that's one. Okay, let's get, now I want other people to have. Okay, Hannah, what do you got for one? You got f5 equals what?
Infinity.
X cubed.
Plus or minus.
Minus.
Now pick any number in the
Any numbers.
That's difficult. I want to say 967.
Okay. So that's another example, but you get the idea. Why are all these examples for F3, F2 through F5, where they also qualify?
Because they all, their first derivative is all equal to 3.
Yeah, the first derivative is all equal to 3x squared, right? So anyway, so that's it. And what that is, that's an example of, let me get over here. That's an example of a constant of integration, why you have a constant integration. And so what we do is we articulate it thusly, and I'll show you the way it works. I'm going to erase to leave myself some space. What we say is the antiderivative of f of x is equal to big F of x plus c. All right?
Where C can
Yeah, and c is an arbitrary constant. So let's work that out. The integral of 3x squared is going to be equal to, what is that going to be? X cubed
be plus
plus c, plus any real number. And so this is an example of an indefinite integral. And you have to be given, as you do this, you don't know exactly what this is going to be. And so where you don't know exactly what it is, you just solve that problem by calling it plus c. And this thing right here that we have is called I'll explain what it is, a general solution. A general solution is where you have that plus c.
Like the plus 4. Okay.
Yeah, and then it could be any of those that you mentioned. All right? So, we come back here and let me go to the next one here. Okay, and here we have an example. Find the general solution of the differential equation dy dx equals 3x to the negative fourth power. So I want you to try a general solution of that, see if you can figure that out.
Wait, what?
Find the general solution and see if you can figure it out.
Yeah, find out, what you'll do is you'll find out,
That's not what you just explained.
find out what you'd have to get here whose derivative is equal to this.
No fun.
So you're going to have to sort of piece backwards and do it. So the way this is set up is to get you mentally activated into kind of exploring through this and sort of thinking through the process here. And while you do that, I'm going to think.
I think maybe I got it. Do you have to put plus C on it?
Well, let me see what you got here.
That's all I got. I don't know if we're supposed to put plus C on it. Oh wait, no, I messed up.
Yeah.
So,
I messed up.
Okay.
I added instead of. Okay.
I want to tell you a step, and I think Aaron is probably on the right track, but what you can do is you cross multiply the dx here. So you have dy is equal to 3 x to the negative 4 dx.
Alright, now I think I got it.
Let me see what you have here.
Is that right?
Negative x to the negative third. That is it. Okay.
that's the answer?
Well, here he's
Because
still working
I did not do
on
the
it.
whole cross multiply thing, I just did it in my head.
So what you're doing here is you go ahead.
Okay.
If you take the integral of both sides here,
No, it's not.
The integral of dy is y.
To actually do it.
On the other side, what you have is negative x to the negative 3 power, and plus you don't know what it is exactly, so you put plus c out here.
Okay, can I?
Yes.
I need help.
Well,
Cause
it's-
I don't know how to actually do it, I just did it in my head.
Did you get that?
Yeah.
Well, you did, okay.
But
Maybe
how?
you're just an anti-differentiation genius.
No, I ain't.
Now, what you do is you're gonna test out what is gonna be ddx,
What is ddx? What does that mean?
means the derivative of.
Is the derivative of?
Then why do you do the whole cross multiply thing?
So if I go ahead, if I take the derivative of this thing right here, then we're gonna take, it's gonna be equal to negative 3, right,
That'd be 3.
times negative 1, because you already have that negative sign out here. And then you're going to have x to the negative 4th power, which is going to be equal to 3x to the negative 4th power. So you can always check your anti-differentiation to make sure. And then, of course, if you have plus c out here, you can take plus c also, but that's going to be 0. So you have that. So by taking the derivative of your antiderivative, you can come back and see if you got back where you started. And in this case, we do see it. And so did you do that? So Aaron and Kylie, did you do that sort of mentally, just mentally what it was?
Yeah, I just looked at it. I was like,
You just
I
looked
get
at
that.
it and figured it out. See, I had to look at it and I had to think through it pretty carefully,
So
looking
we're
at it.
solving
Backwards.
backwards.
It's doing the opposite of
like-
differentiation.
So
Yeah.
what's in the middle is what we were doing, because, yeah.
I don't know.
And
that
so,
I was just confused on why.
do you remember the-
In the question.
I didn't wear the calculus t-shirt today. I might wear it tomorrow. Remember I had that calculus t-shirt with the chicken and the egg? Remember
Yes.
that? I'll wear it tomorrow.
I don't
Maybe.
get the whole like cross multiplying the like dx thing.
Yeah, what it is you have this dy divided by dx, and so if you cross multiply the dx here, that's how you get that. You take the integral on the left side of dy, it's just going to be y. And so this is solved by integration. So anyway, that's where we are in the course, and it's sort of the introduction to integral calculus. Welcome to integral calculus.